Okay, after learning about the characteristics of waves, the speed of waves, how to draw them as rays and wave fronts, it's now time to talk about the properties of waves. So anything that behaves like a wave reflects, refracts, and diffracts. Those are three things. So if I see a particle behaving like a wave, it must reflect, refract, and diffract. And that's going to be the topic of the next few videos. Okay, so reflection, as you know, I'm sure you've covered a lot of this stuff in grade 9, but reflection occurs when a wave hits a boundary, such as a wall or a change in medium, and that wave, here are the wave fronts and the ray, that wave would reflect, and the angle at which it approaches is going to be equal to the angle that it reflects by. Okay, this line, dotted line in the middle, is called the normal line because it's perpendicular to the surface. And that's our reference point. So when we're talking about an angle at which the ray comes in, we're talking about this angle, the angle between the normal line and the ray. Okay, so that's my angle of incidence. That's my incident angle. And this would be my reflected angle. And both of those would be the same. That's the law of reflection. Okay, refraction is a property when light changes or wave changes its speed. As a result of that, it appears to bend. So we have light going from one medium into another medium, and as a result of that, it bends, it slows down. And we can see that there's a lot of changes in those waves. Then, if a wave goes through an opening, the wave tends to go around corners. That's called diffraction. Okay, the wave spreads out as it goes through an opening. You can imagine if you threw a basketball through that hole, it wouldn't spread out, it would just go straight through. So waves have that property that they spread out through openings. So this, as a summary, is reflection, refraction, and diffraction in a nutshell. And we're going to learn a little bit more about the calculations and what's involved in each. Okay, so reflection in the IB curriculum is actually pretty simple. We don't do too much with it. We just have to know how to identify it. So you always get reflection when a wave hits a surface, okay? Or changes its speed or goes through a different medium, okay? So here I have a wave coming in, coming out. Here are my wave fronts. They stay the same on both sides. There's been no changes. And the angle of incidence is always equal to the angle of reflection. That's the law of reflection. All right, so we do this all the time when you stare at the mirror and you look at your feet in the mirror. What you're really looking at is sunlight reflecting off of the feet onto the mirror surface and to your eyes, okay? And that angle at which that light hits the mirror is going to be equal to the angle that that light is going into your eyes, okay? Now, there's some basic problems that we could do is where if I gave you the distance that you are away from a mirror, okay? If I told you that distance, you'd be able to then do some trigonometry to calculate, for example, the person's height, okay? Or you can calculate the depth of the image that person is going to see. Those are things that you would see in example problems in a book or somewhere else. But we're not really going to cover that in this video. Okay, but the big thing that we're going to cover in this video is something that I know you guys covered with Mr. Sickles, is refraction. Okay, so refraction is the apparent change in direction of a wave as a result of a change in speed. Usually it occurs due to a change in medium. So when something is going from air to glass, or when a wave is going from deep water to shallow water, you start to see a change in its direction, okay? And that's due to refraction. So here I can see a picture of water waves in the sea. Okay, in the deep sea, the waves have an equal wavelength and they're all traveling in the same direction. But as they approach the shore, we see that the waves start to bend and they get shorter. Okay, and that's because they're slowing down. All right, so that change in direction is a result of refraction. Okay, here in this diagram, you can see that in the deep water, all right, the wavelengths are all constant and large. And then as it hits this shelf, okay, where the beach is starting to approach, it gets shallower and it slows down, as I presented in the speed of water waves before. Okay, and we know it slows down because you can see that the wavelengths are getting shorter. All right, so the direction of that wave, that's my ray, has changed, okay, and that's refraction. All right, so as we can see here, the waves got closer together as it slows down, so the wavelength would get shorter, and in that case, we would see a change in direction. All right, so in addition to waves, water waves, which we can see refraction if you go to the beach in Ghana, we know that light waves also undergo refraction, and that usually happens when they change a medium, when water is going from air into plastic or air into water. Okay, we'll see this bending effect. All right, so this ray of light, this laser being shot into a, let's say this is a plastic brick, okay, you can see that it changes directions and then comes back with the same angle at which it came in. Okay, and that apparent changing or bending is refraction. All right, this little dotted line in the middle is my normal line. Okay, and if I wanted to figure out what my angles are that I'm going to be talking about, this angle here would be my incident angle, and that angle down there is going to be my angle of refraction. Okay, so we can see that the incident angle and the angle of refraction are different. All right, and then if I wanted to see my incident angle over here, or that angle of refraction, that angle over here is going to be the same as that angle over there that's coming in. Another area that you have seen refraction before is when we form rainbows. When white light, which is composed of all the different visible wavelengths of light, when white light hits a material, okay, it's going to refract if it slows down. And then every color starts to appear. That's called the dispersion of light. And the reason that the colors start to separate is because different wavelengths of light slow down to a different degree. All right, so they would have a different angle of refraction. So these are just general things that we talked about when we're talking about refraction. But I can specifically calculate those angles of refraction using a simple law called Snell's law. And that's what we're going to be doing right now. Okay, but before doing that, just one more image. Okay, this is a very classic image that you'd see if you searched up refraction. You're always going to get this idea. And refraction causes optical illusions. I'm sure with Mr. Sickles, you saw a pencil in a glass look like it's broken. And this is very common when you look at something underwater, like a fish, and you see a fish and you try to grab it, you're going to miss it. Okay, because what you're actually looking at is an image of the fish, not the real fish. When light reflects off of the real fish, it's going to go through a medium change, and that light is going to change speeds. As a result of that changing of speeds, it refracts. But your eyes have no idea that it refracted, so it just follows that ray and imagines it came from a certain point. So if you're spearfishing and you go for the image of the fish, you're going to miss it. What you have to do is go before that image and deeper, and then you will catch a fish. So Bear Grylls has done a lot of videos about that. All right, so let's talk about the math of refraction. Okay, because that's what we're after. How can I calculate these angles? Well, Snell's law of refraction says that the angle of refraction is greatly dependent on the speed of light in the medium. Okay, and more importantly, it's greatly dependent on the change in speed. The greater the change in the speed when I go from one meter to the other, the greater the bending of the light. Okay, and that's what we're going to look at. So this mathematical relationship here, n1 sine theta 1 equals n2 sine theta 2 is what you'd see in your textbook. Okay, but before doing that, we need to figure out what these variables are. Okay, so if the light is originating, let's say, in water and then refracting out of the water, okay, this is my angle of incidence. So theta 1 would be my angle of incidence at that barrier. This is my normal line. Okay, and theta 2 is my angle of refraction. I got that. I know what sine is, but what is n1 and n2? Let's get to that right now. So every medium has a refractive index, okay? And what a refractive index is it's the ratio of which that's the speed of the wave in that medium changes, okay? So the refractive index of a medium, the refractive index of a medium is equal to the speed of light in a vacuum, 3 times 10 to the 8 meters per second, divided by the speed of that light in the medium, okay? So light in this medium, in water, actually travels slower than the speed of light, okay? That's because the light is interacting with molecules in the medium, the electric fields of the molecules in the medium, and it gets slowed down, all right? So we've classified all materials with something called a refractive index, and that tells us the change in speed in that medium. So 3 times 10 to the 8 meters per second divided by the speed gives me a number, okay? And here's a table showing the refractive index of different materials. So a vacuum where there's no molecules, the speed in that medium would be 3 times 10 to the 8 meters per second. Okay, it'd be the same as it is as regular speed of light. Okay, in air it's almost 1, but there's molecules are spread out, so it still interacts, so it slows down just a little bit. But in things like diamond, which are really dense, some of the densest materials on Earth, okay, it slows down by a lot. So any number greater than 1 is going to have a speed that is smaller than the speed of light. And you can see here on the right, the greater the density of the material, the greater the speed, the greater the refractive index, and the slower the speed in that material. Okay, so n in Snell's law is refractive index, and I can find the refractive index of all materials in a data table, or they'd give that to me in a problem. So going back, let's take a look at Snell's law. Okay, so Snell's law said that the greater the change in speed, the greater the change in angle. So another version of Snell's law just has the ratios of speed. So sine of my incident angle divided by sine of my refracted angle is equal to the speed of my wave in the first medium, the incident medium, and the speed of the wave in the other medium, okay? Which is also equal to, now I'm going to show you in a second, if I can get a better pen, a little thinner than what I have going right now, okay? Which is going to be equal to n2 over n1, and I'll explain why. So sine theta 1 over sine theta 2 is equal to n2 over n1. If I rearranged this formula over here, I would get that formula. So how did we get that relationship? Well, if I would actually substitute the speed of light divided by the velocity in medium 2 divided by the speed of light divided by the velocity in medium 1. Do you see here, that's what the refractive index in medium 2 is, and that's what the refractive index in medium 1 is. Then what I can see is that the speed of light cancels out, and I'll be left with v1 over v2. All right, so we have a relationship. This is in your data booklet. This is what you actually have inside of your, oops, I'm just gonna fix this. This is what you have in the IB data booklet, which is going to be equal to n2 over n1, which is equal to v1 over v2, okay? So combining any of those variables, if they gave me the velocity of the light in the medium, if they gave me the refractive index in the mediums, I'd be able to calculate the refracted angle and so on and so on and so on, okay? So let's go do some practice problems, okay? Here I just did that again. I just showed you how we got that relationship. So let's do some sample problems really, really quick. Okay, so how do I calculate the refractive index of a material for which the speed of light is 2 times 10 to the 8 meters per second? Okay, so we remember that the refractive index of that material is going to be equal to the speed of light divided by the speed in that medium. Okay, and then that would give me 1.5. So a refractive index of 1.5, if I go back up to this table, is glass. Okay, so glass, that's typical of glass. So that would be what the speed of a wave would be in glass. Okay, now the next problem I want to cover is a laser light is incident from water into glass at an angle of 70 degrees. Okay, describe the behavior of the light ray as it travels from water into glass. Okay, so it's going to bend because glass has a different refractive index than water. It changes its speed. And according to this refractive index, the speed of that wave slows down, okay, because it's more dense. All right, as a result of that, I see that it bends, but it bends towards this normal line. Okay, whenever light slows down, it bends towards the normal line. Okay, whenever light speeds up, it would bend away. Okay, that's an important thing to think about. Okay, so that's how we described it. But what I also want to do is I want to calculate the angle at the bottom there. What would the angle of refraction be? Okay, so let's go revisit those formulas. Sine theta 1 over sine theta 2 is equal to n2 over n1. All right, so I'd be able to calculate the theta 2, which is what I'm after. All right, so we're after this. We want to find the angle of refraction. So I have to rearrange these formulas. Okay, I want to put this over here, and I want to rearrange everything to solve for it. Okay, so sine theta 1 times the refractive index of the first medium divided by the refractive index of the second medium is going to be equal to sine theta 2. Now that we've rearranged the formulas, I can plug everything in. Sine of 70 degrees times 1.33 divided by 1.51 is equal to sine of theta 2. And then if I do the inverse sine of everything that's above, I will get 55.5 0.9 degrees, okay? Something that I've solved before doing this, so I didn't waste our time, okay? So that means that the angle of refraction is 55, let's change the color so you can see it. The angle of refraction is 55.9 degrees, which is smaller than the angle of incidence, which was 70 degrees. And that's what we would expect because the light is slowing down, okay? So remember, when light slows down, it bends towards this normal line. When it speeds up, it bends away. Very, very important to remember, okay? So here would be a typical challenge problem where we're looking at a virtual image, okay? What we want to do is the fisherman sees an image of a fish, but he knows that that's not the real fish, okay? So what we want to be able to do is calculate using all these angles that we have here, what is the actual position of the fish so that he can go catch it, okay? This little line here is my normal line, and so what this question is asking is to calculate the actual depth of a fish below water, assuming the following things, okay? So what is the actual depth? How deep is that water, okay? We know that that actual fish is 2 meters away from this normal line, so using that information, I should be able to calculate my actual depth. In order to do that, I want to try to do trigonometry. If I have this side, I'd be able to solve that side, which is the actual depth, by solving that angle. That's my reasoning, okay? So what I need to do is I need to apply Snell's law to find what that angle is, okay? So first of all, the refracted angle, angle 2, this is the refracted angle. See, that's the light is originating here. That's my incident angle, and that's my refracted angle, okay? So my refracted angle is 30 degrees, okay? That's what the fisherman is looking at with respect to the normal. Okay, so that is our 30-degree angle over there. So if I know that, and I know my refractive indices of the materials, I should be able to solve the angle here and then do some trigonometry. Let's go do that. Okay, so sine theta 1, okay, which is this angle right here, sine theta 1, divided by sine theta 2 is equal to n2 over n1. That's Snell's law. So sine theta 1, which is what, no, we're not trying to solve for, we're trying to solve for sine theta 1, is equal to n2 times sine theta 2 divided by n1. Okay, so sine of theta 1 is equal to 1.00. Why? Because this is n2 and this is n1. Because that's the medium that I'm going into. N1 is water. 1.0 times sine of 30 degrees divided by 1.30. Okay, that incident angle is going to be 22.6 degrees, something I solved already. Okay, now that I know my incident angle, all right, I can then do some trigonometry. So that's my actual depth. I'm trying to solve for x. This is 2 meters. That is 22.6 degrees. So this is opposite and that's adjacent. So I can use a tan function. Tan theta is equal to 2 meters over x. So tan of 22.6 degrees is equal to 2 meters over x. So x is going to be equal to 2 meters divided by tan of 22.6, which is going to be equal to 4.8 meters. Okay, so my actual depth is 4.8 meters. Okay, now that would be an application of Snell's law to be able to solve something such as actual depth. That would be an extra step in a problem that you'd expect to be at a little bit of a higher level difficulty. Okay, I'm going to do one more video of solved problems just to get you used to applying Snell's law, but that's basically it for refraction. All right?